Hello. In this lesson, we're going to be talking about polynomial functions. So first, we're going to define a few characteristics of polynomial functions. The domain includes all real numbers, so it goes from negative infinity to infinity, all of them. The graphs are smooth and continuous, so they look something like this, for example. And all terms have positive integer exponents. So if we take, for example, f of x equals 2 times x to the power of 4 plus x, this is a polynomial function because all of these exponents are um, positive. Now, if we do, for example, g of x equals 2x to the power of negative 4 plus x, this one is not a polynomial function because of that negative exponent 4. We can rewrite this with a positive exponent, but see how that positive exponent goes under the um, a line, the division line, the fraction line. So it's in the denominator. So this is an example that is not a polynomial function. So all the exponents have to be positive integers. And then what we're going to look at here in a little bit is if f of a and f of b have opposite signs, there is a 0 or a root. This is the same thing. 0 and root are the same thing between them. And then greatest possible number of turning points is no more than 1 less than the degree. So let's move on. We're going to be learning about those. Intermediate value theorem, IVT. Suppose that f is a polynomial function and a, b, both included, is an interval for which f of a does not equal f of b. If L is a number between f of a and f of b, then there is a number c in the interval ab such that f of c equals L. Okay, we'll look at what that means in just a little bit. We're going to first graph f of x equals x cubed. So let's do a table here, and we're going to do -2, -1, 0, 1, and 2 for x's. So when we plug in -2 here, -2 cubed is -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. Now we can start plugging in the points. So we have -2 and -8. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8 right here. -2, -8. Next one is -1 and -1. Right there, we have a 0, 0. And then we have 1, 1. And we have 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. Something like this. Okay, so that is our y equals x cubed. Now, what we're going to next look at is the degree of a polynomial function. So if our function is f of x equals a x to the power of n, the n right here is the degree. It's always the highest degree of the function. So for our example here, the degree is going to be n equals 3 because that is the highest degree. Next, we're going to look at maximum number of turning points. So the total number of turning points. sometimes you hear or see the word peaks and valleys. On a polynomial function of degree n is at most, notice the word at most, n minus 1. Okay, so let's go back to our example here. So maximum number of turning points, n minus 1, our n is 3. We're going to subtract 1, so 2 is the maximum number of turning points. And if we look at this, this one actually, yeah, we'll talk more about the turning points. Let me not say anything right now in a little bit so that I don't confuse you. But anyways, so all we did was just define what is the maximum number of the turning points. Okay, next we're going to look at determining the end behavior. So because the domain of a polynomial function includes all real numbers, most of the function exists to the far right and left. As the function either increases, which means rises, or decreases, falls without bounds. Okay, leading coefficient test. Used to determine the end behavior of the polynomial function, examine the leading term LT of the function when not factored. So f of x equals a times x to the power of n. The a here is the leading term. Or sometimes you'll hear leading coefficient. Okay, so let's look at a few examples here. We're going to sketch them at the same time as we look at them. So our first one is going to look something like this. Now, what this has is so the leading term is greater, why can I not draw a greater, there we go, greater than 0. And if we look at this and compare it to the one that we just graphed, they look very similar. Our degree in the example is 3, so here n is odd. So our examples for this one would be f of x equals 2x cubed. Again, a is greater than 0, the 2 is greater than 0. We could do g of x equals 0.05 x to the power of 7. Again, this is greater than 0. And our n, which here is 7, is odd. Another example would be, for example, 1/5 x to the power of 9. Again, the 1/5 is greater than 0. It is not a negative or a 0. Okay, next one, we're going to look at what happens when a is less than 0. And we are going to keep n as odd still. So what actually happens is that it comes from the left and goes down like this. Think about, if you're struggling with these, think about a straight line. If we have y equals x, our degree here is 1, which means that it is odd, right? So when our leading term is positive, so LT positive, so, or let's do it the way. So a is greater than 0, the line goes this way, right? Uphill. If we have y equals negative x, which means that a is less than 0, that is when the line goes downhill like this. So it's basically the exact same thing here, even though we have a different, a higher degree of a function. So examples for this would be f of x equals negative x cubed, or for example, g of x equals negative 5x to the power of 9. The key difference between these first two examples is that positive and negative leading term. Okay, next one, we're gonna here say that the leading term is a 0. We're gonna switch in to be even. So we had odd in the first two examples, now it's gonna be even. Well, if you think about f of x equals, for example, half x squared. This degree is 2. It's it's an even degree, and we know how to graph a quadratic function. It's going to be an upward opening parabola. I did not graph that one. I just graphed an example or sketched an example. We could have g of x equals 3x to the power of 4. As long as the a is greater than 0 and n is even here, all of those are options for this one, or examples for that one. Okay, let's look at when a is less than 0 and n is even. So if we think about, for example, f of x equals negative 2x squared, what happens with it? It opens downward, right? That's a downward parabola. Other examples for this one could be, for example, negative 0.2 x to the power of 8, or h of x negative 5 x to the power of 6. All of these examples, they have a negative leading term. Should actually not put a negative leading term and even exponents. Okay, so give the end behavior degree and maximum number of turning points. Again, our degree here is 3, which means that it is odd. Our a is 5, that is greater than 0. So when we go and look at when a is greater than 0 and n is odd, it's this first one here. So our endpoints are going to be going down to the left and up on the right. And then we're going to do the maximum number of turning points here on this last one here. So the maximum number of turning points is going to be the degree minus 1, which is 2. Okay, let's look at this next example. And now, remember that when we're doing these, we want to make sure that the highest degree is the first term. Like here, yes, n is the high, or 5 is the highest or largest exponent, so it is the highest degree, so it's going to be n equals 5. We still have an odd. Now our a is negative 8, which means that that is greater than 0. So we're going to, the left side is going to go up and the right side is going to come down. Maximum number of turning points, the degree 5 minus 1, which is 4. Okay, next one. Again, this is the largest exponent. So our degree n is going to be 5, which not 5, 4, which is even. And our a is 9, which is greater than 0. So our n's are going to go the same way. So every single time it's an even, the n's go the same way, same direction. And since the a is greater than 0, they're going to go up. Our turning points are 4 minus 1, which is 3. Okay, next one. Again, we have to make sure that the largest exponent is first, so our degree n is going to be 8. That is still an even. Our a is -6, which is less than 0. So we have an even, which means that the ends are going the same way, and since a is negative, they're going to go down. Maximum number of turning points is going to be 8 minus 1, which is 7. Okay, so why are we doing this? It's because after we have all these, we're actually able to sketch, um, polynomial functions with higher degrees based on what we know here. We need one more thing to know what happens in between, which is behavior at the intercepts. Now, these are also called roots or zeros. So that's the exact same thing when the x-intercept is the same as a root or a zero. So every x-intercept corresponds to a factor of the polynomial function where x minus a inside parentheses to the power of k. So theorem, let a be the root with multiplicity k for the polynomial function. And again, notice that when a is the root, this is a negative, but the a is going to be a positive. We'll look at that. So if k is odd, the graph crosses the x-axis at a0. If k is even, the graph touches at a0 and turns around. Okay, so let's look at example. So now we're going to actually look at all these and then we're going to sketch it. Okay, in this example, it looks a little bit different. So we already have it in a factored form here. We can still look at what is our, highest degree in this case. And now we need to look at it in a little bit differently, because if we multiply all these out, the highest degree is whatever is the largest exponent at that point. So we have a degree of 2 and we have a degree of 1. We actually, what we're going to do is we're going to end up adding those two. So 2 plus 1 equals 3. That is going to be our highest exponent if we multiply these out. And that's our degree as well. So our degree is odd. Our LT right here, there's no numbers in front. So it's a 1. So degree is odd and our A is greater than 0. So that means that our N behavior is going to be left down and right up. Our maximum number of turns is going to be 3 minus 1, which is 2. And now, for us to sketch the graph, we're going to need x-intercepts. We need to know where does it go. So, or where does it cross the x-intercept? So we have x minus 5 squared times x plus 4. What we're going to do is we're going to set this to equal 0. So by the zero product property, we can say that x minus 5 squared equals 0 and x plus 4 equals 0. Now, to get rid of that squared, we take a square root. Well, square root of 0 is going to be a 0, so we just end up with x minus 5 equals 0. You can skip that step and just write x minus 5 equals 0. Or x plus 4 equals 0. So there should be the word or in between. Now, we're going to solve these. So add 5 to both sides, and we get x equals 5. We subtract 4 from both sides here, and we get x equals -4. So now we know that we have an x equals 5. and x equals negative 4 as our zeros. So now we need to look at what did we say here. If k, and k is the exponent here. If k is odd, the graph crosses the x-axis. If k is even, the graph touches. So k for x equals 5 is a 2, which is even. So that means that it touches and turns around. For x equals negative 4, it crosses and goes through. So let's do 1, 2, 3, 1, 2. I'm going to put 5 here. So I'm going to count by 2, 4, and 6, 8. So 5 is in the middle. And then we're going to do negative 2, negative 4, negative 6. And it crosses at negative 4 again. Now, remember, we talked about the end behavior here. So it starts from the left. It crosses at x equals negative 4. So it's going to come through here and keep going up. Now, one thing that we can check here still, and what we've been doing with in the past, is where we've calculated the y-intercept. Remember that when we do that, we plug in x equals 0. Okay, so y equals 0 minus 5 squared, 0 plus 4. Negative 5 squared times 4, 25 times 4, which is 100. Well, okay, so our point would be 0, 100. Are we able to graph that in here? No, we're not. So we're just going to kind of sketch that it keeps going, up and up and up. Then it's going to come down. Again, at x equals 5, it touches and turns around. So it comes down, touches, and turns around. And look at our endpoint. Ends are going where they're supposed to be. One to the left and one to the right, which we figured out over here. So that's our sketch for this graph. Okay, let's look at this next example. We have a little bit more factors here. So we've got g of x, which is x plus 5 cubed, x minus 3 squared, and x plus 1. We're going to calculate the degree n. We're adding all the exponents, 3 plus 2, and again, remember that there's a 1 over here. So we get 6. That means that this is even. Now our LT, so all of these x's, the coefficient is 1. So our leading term is going to end up being 1, which is greater than 0. So what does that tell us for the end behavior? If our a is greater than 0 and our degree is even, it means that both ends are going upward. So now we're going to calculate the max number of turns. Our degree n is 6. We're going to subtract 1 from it, and we get 5. Okay. Next, we're going to go ahead and do the zeros. So the x-intercepts the roots. We have x plus 5 is the first one. If we set that to equal 0, we get x equals negative 5. Now, the multiplicity, so the k here for this one is going to be 3, which means that it is odd. So that means that this one crosses the x-axis. Okay, our next factor is x minus 3. We're going to set that to equal 0. So x equals 3. The k for this one, the exponent is 2, which means that that's an even. So the graph touches and turns around at x equals 3. Then we have our last one, x plus 1 equals 0. So x equals -1. For this one, our k is 1, so that is an odd. So that means that it crosses. So we have -1, 3, and -5. So I'm still doing these by 4, like this. Okay, let's see if we can get anything with our y-intercept to help us kind of know where we are. So 0 equals x plus, no, that's not the way we do it. X equals 0 when it's the y-intercept, so y equals 0 plus 5 cubed times 0 minus 3 squared times 0 plus 1. So y equals 5 cubed, which is 125, times 9 times 1. Well, that's going to be a large number when we do 125 times 9. There's no way that we're going to be able to graph that. Actually, that's not. Y equals 1,125. So our y-intercept is 0, 1,125. There's no way we can graph that. Okay, so we know that our ends go the same way. They're going both up. So the first place where it crosses is x equals -5. So we're going to start from here, come down. We don't know how far it comes down. We're just going to sketch something here. Our next one is -1 where it crosses again. So it comes down here. It keeps going up. Remember, it goes all the way to 1,125 where it turns around. And then it touches at x equals 3. So it's going to come down, touch, and turn back. And if you can tell that the ends are going both up. So we graphed it the correct way. Okay, so now next we're going to look at roots with multiplicity greater than or equal to 3. And they cause the graph to flatten out at that root. So if we think about, for example, x squared, x squared looks something like this. X to the power of 4, actually, you know what? Let me do a better one. It touches and goes back up like something like that. X to the power of 4 comes down the same way, but it's flatter over here, and then it goes up again. Okay? F of x equals x is a straight line, like, oops, that did not go through origin. Is a straight line through the origin, like this. X cubed, we just graphed. We know that we've got these points that it goes through somehow. A little bit of a curve here, like this. Well, x to the power of 5 is going to look very similar, but it's going to be flatter right here. Like there's going to be a more of a flat surface. So that's what this roots with multiplicity greater than or equal to 3 cause the graph to flatten out at that root. Okay, let's look at more examples. So we're going to give the degree, the end behavior, and the maximum number of turns and sketch the graph. Feel free to pause the video and try these on your own, and then continue to see if you got them correct. Okay, f of x equals x to the power of 4 minus 4x squared. So our degree here is 4. Our a is 1, which is greater than 0. The degree is even. We know that the ends are going to have to go both up. And that our max number of turns is going to be that 4 minus 1, which is 3. Next, what we want to do is we want to find the x-intercepts here. X to the power 4 minus 4x squared equals 0. And to know what our goal now is we want to have them in this form right here. So we want to have them in the factored form so that we know what the multiplicity is, so that we know if it touches or turns around. So greatest common factor here is going to be x squared. What's left is x squared minus 4 equals 0. X squared equals 0. That's going to be x equals 0. And then x squared minus 4 equals 0 is we move the 4, so x squared equals 4, and we take the square root, which means that we get a positive and a negative, so x equals positive and negative 2. So x equals 0 is going to be the origin, and now that multiplicity 2 is even, so we know that that's going to touch and turn around. Now, for this x squared minus 4, this factor, the exponent is 1, so it is odd, so it's going to cross at x equals negative 2 and x equals plus 2. So here is our negative 2, and here's our 2. Again, our end behavior is right here. It comes down, crosses, touches, goes down, crosses, and goes up like this. That's the sketch for this graph. Okay, let's look at g of x equals x minus 3 to the power 4, x plus 2. Our degree here is 4 plus 1, again 4 and 1 here, so n equals 5. Our a leading term is going to be 1, that is greater than 0. So this is odd, and that is greater than 0. So our end behavior is going to be down left and up right. Our max number of turning points is going to be 5 minus 1 equals 4. So if we look at the number of turning points here, we had 3 turning points, the maximum number. 1, 2, and 3 are our turning points. That's how we know that if we had a 4th turning point here, we knew that that would be wrong because we end up with 3 turning points. So the same thing here, maximum number is 4. It doesn't mean that we're going to have 4. It just means that that's the maximum number. Okay, so let's go ahead and see where the x-intercepts are. So x minus 3 to the power of 4 times x plus 2 equals 0. So x minus 3 equals 0, x equals 3, or x plus 2 equals 0, x equals negative 2. X equals 3, for that, our k is 4, so it touches 1, 2, 3. Let's put it here. For x equals negative 2, our k is 1 over here, so it crosses. So negative 2 right here. We start from the left down. And actually, let's do the y-intercept just in case we get one that works. So y-intercept x equals 0. Y equals 0 minus 3 to the power of 4, 0 plus 2. I don't think so. Because when we do this, 3 to the power of 4 is going to be 81 times 2, which is 162. Yeah, so that's not going to be sketchable. Okay, so we're going to go up here to the 162, then come down at 3. It touches and goes the other direction. So that's how you graph that. Again, please don't hesitate to ask if you've got any questions about this. Bye.